Well, the next case we're going to look at here is the side-side angle condition. We're going to see what that tells us. Okay, so we're going to start with the exploration by sliders. Again, I'm using Wesley Clark's sketch here. And so let's start with side angle. So it's angle. We're actually going to think of it as angle side. So we start with an angle. Okay, angle A, and we go out on the side next to it a certain length. Let's start like this. A certain length here. So this is your first. This is your side 2. Side 2, the second one listed, if we were listing out the measurements, is going to be the one that's adjacent to the angle or part of the angle. So we start by making our angle. That gives us this angle here at A. Slider Z then is going to control the length to get to point B. Now, then side 1 is the radius, is how far we're going to get for the other side. So we know point C has to satisfy two things. Number one, it has to be on this ray here to make the angle at A right. And number two, it has to be on this circle right here to make this length right. Now, it's possible that we can have a situation like this where it's just too short and those two things don't intersect. Exactly the same setup is over here. We have an angle, okay, and that specifies this angle here at A first. Then we specify a length here for the side from A to B, from that side, for that length. And then we specify a length for the other side by this circle here, by this slider here, which gives us the length of the last side. Let me experiment with my spacing here just a bit. Okay, so okay, so the same situation could exist where this thing is too short and it doesn't reach. So that's sort of the first case, is that there is a no solution case if the measurement is too short for the green length. Now, if the green length is a bit longer, and if you can match it up just exactly right, it's going to be really hard to get it exactly right here, but I'm almost there, not quite, but almost. If you match it exactly right, this circle and this line are tangent to each other at this point here. They touch exactly once, in which case you're going to have a right triangle with a right angle at point C. And that's going to be exactly one case. And that's going to be the same thing that goes over here. If this is exactly the right size, there'll be exactly one triangle here. And again, these curves here are tangent, this ray and this circle, okay, in hyperbolic geometry, or two arcs of circles in Euclidean geometry. They're tangent to each other, so again you're going to get a right angle there between or at this point C. Now, if it's a bit longer though, you get two possible intersection points, and I'll make that over here one that's a bit longer. So this one is the one that's called the ambiguous case. And because of this possibility, the side-side angle condition is by itself, without any further explanation or any further information, is not enough to guarantee that you have one congruence class of triangles. So you could have, depending on the measurements, 0 congruence classes, 1 class, or 2 classes. No more than that. but you do get two classes. Now, one thing that's interesting about this is this right here is an isosceles triangle from C1 to B to C2, and in fact that makes these two base angles congruent, something you'll prove. And so this angle at C2, the two angles at C2 form a linear pair, and so they're supplementary, which means this angle C2, which is the angle of the triangle, the interior angle of the triangle ABC2, or compare that to the interior angle C1 of the triangle ABC1, those two angles have to be supplementary. Okay? Same thing works in hyperbolic geometry. These two angles here are supplementary, so this one and this one are supplementary because these two are congruent. Same proof exactly. So, it turns out that if the two triangles are not congruent, then the two possible angles at C are supplements of each other, supplementary angles to each other. Okay? Now, if you can get this longer still to where it gets the same length as the blue length, or longer yet, then you'll see that this circle now goes back and it only intersects this line, that ray, in one point. If it would intersect the line at another point over here, but that's not part of the ray. And so now we're in a situation where we're back to one triangle possible again. So if we make this radius the same as or longer than the other one, like this, for example, now we're down to a situation where again these two, this ray and this circle will only intersect once. The rest of this line coming down this way would intersect it, but it's not part of the ray. So you're back to a one solution situation, one congruence class of triangles, and then this situation happens exactly when the first S, the green length, is the greater than or equal to the blue length, this second S. So that sometimes we call the capital S, lowercase s, capital A situation. So it's SSA plus another bit of information, and that other bit of information is enough to narrow it down to one single case, and that does guarantee congruence of triangles. You can do the same thing in the same kind of setup works in spherical geometry. Let me see if I can show you that in this elliptic disc version. So let me start. Whoa. I want to get rid of all that. Alright, so let's start here by see if I can show you an example of this. So we start with a segment here, and we specify an angle by making a ray. Well, there's part of a whole line, not a ray, but a line. Did it have a ray thing? Okay, it doesn't have a ray, but if we put this at the equator, then it's showing actually a ray there. Okay, and so we have a specified length here. And so we have two of our points, let's say A and B, and we've specified a specific angle. Now, if we build a circle, we take an arbitrary point here where we don't know, well, I'm sorry, not that. We have our point here. We want to build a circle here, now center and point, where it's centered here and going out here. Now, so if the radius of this circle is the length of that first side, the blue length is the length of the second side, and this angle is specified. Again, it can be too short, it could go out and meet in two places, or if it's longer, If it's long enough, then it will only meet, it may not, actually there may be a situation where there's no solution, or where it goes back and touches once. But basically we have a situation, we do have this ambiguous situation here where that and that are congruent. Okay, but then your other segments, one of them goes here and one of them goes from A all the way to P, and we see that this is those two triangles clearly are not congruent. Okay, and there is a case somewhere in here where this is exactly tangent, and so there's one solution, there's a two solution, there's a no solution. So we have at least those three possibilities on the spherical geometry, and it's going to basically we're going to be able to do exactly the same thing there. So we have more or less the same conditions there in spherical. So the SSA condition by itself is not quite enough. In this one here, we can enter parameters and get it to work out. And let's go back to, for Euclidean geometry, let's go back to my sketch here. SSA 1 basically shows the same construction here, where we specify really we're going to do it the angle first, then we specify out how far out to go here, and then how far out to go for this radius. And again, there's no solution, one solution, two solutions, and then back to one solution again, depending on the length of this green one relative to the other two. Now let's look at this with putting in some numbers. So we can put in some numbers here. Let's let A be 4. Let's let B be 6. And let's let the angle be 60 degrees. And we see that we can see that there's no solution in this case. Okay, if we let this be a little bit bigger, let's let this be 5. And let's let B be, let B be 5, and this one be 4, then it doesn't reach. Let's let this be 30 degrees, and let's let this one be, let this one be 10, and this one be, let's let this one be 8. Okay, there's an example where we're in the one situation, one solution situation, where it's a right angle right there. So that's tangent, and there's exactly one solution. Okay, but if we make A a little bit shorter, even just a little bit, 3.5, it doesn't reach. Make it just a little bit bigger than 4, let's make it 5, and now we have two different points of intersection there, and we've got two different ones. Okay, and so we have, again, how would we go about doing this? We would start by making our angle. It's 30 degrees. We construct our adjacent side, the B, which is 8 centimeters. Then we take our compass and set it the length of the A, 5 centimeters, draw a circle at C, and see where that touches. In this case, it touches the ray down here at the bottom. It touches that ray twice, so there are two possibilities for B. Possibility 1, where we have an acute angle here. Possibility 2, where we have an obtuse angle. So there are actually two complete triangles. One triangle is here's the interior of it. It's got an area of about 19.86 square centimeters. This angle at B is obtuse. I'm sorry, this angle at B is here. It's acute at 53.13 degrees. and then the side, which goes all the way from A to B1, is 9.93. The other possibility is the triangle that's over here, and it still has both of these triangles have the AB and the capital A the same, and we see different measurements here. But if you look at both of them, you're going to see some interesting things. Of course, they share the side B, so that's the same. They share the angle 30 degrees, and they have two sides that are congruent, the red sides. So they have the side-side angle condition, but they're not congruent. What is interesting, though, is that these two are supplementary angles. If you add those up, you get 180 degrees. We get different C2s. We get different angles here for C as well, and we get this. Okay? Now, which case is which? Let's look at this a little bit. So, let's look at an altitude here, a perpendicular. Now, when are we going to get a no solution case? Well, the no solution case, remember, is when this is too short. So like 3.5, it was too short. Okay? Okay? And that's when it was less than that altitude. If it's just right, then we get one solution. And so both of these triangles are really the same. It's not really two triangles, it's one triangle. And that happens exactly when the A is the same as the H. So what would the H be? Well, if we know the angle A and we know the side B, we know this side H is, if we do H over B, we get the sine of angle A. So H is B times sine of angle A. And so if the A is less than that, A is less than H, or B times sine A, then A is too short to reach the ray and no triangle is possible. If it actually equals it, there's exactly one triangle solution, one congruence class of triangles, with a right angle at B, and B and X are the same thing. But if it's a little bit longer, let's say 5 here, then we got the ambiguous case. Okay? But if it gets longer still, up to the side of where the for the first one is bigger than the second one, or equal to it, if this is 8, there's only one solution there. And or if it's bigger still, like say 9, we're back to one solution. Okay? And that is, we just get the one triangle there. And that's going to be if A is greater than B, or equal to B. So the ambiguous case happens when A is between H and B. So A is greater than B times sine of angle A, but less than B. That's exactly when you get the ambiguous case. Okay? Now, can we solve this? Well, in the Euclidean case, yes we can. Let's go back to an ambiguous case 1. Let's go back to 5. Let's go back. Let's make the whole thing a little smaller. How about that? There's a good example. Okay? Well, we can use law of sines to get the measure of angle B. So B is the inverse sine of B sine A over A, or B is pi minus the inverse sine of B sine A over A, or in degrees, 180 degrees minus that. And so we work this out and we get two possibilities. Now, if there's something, so these are the two things you have to consider, or in other words, just figure out B1 and do 180 degrees minus that to get this. Okay? Now, if we add these, the acute one's always going to be a possibility if this is, well, in the case where it's too short, this will give you, this thing inside here will give you something that's undefined, because it'll give you something that's not between -1 and 1. Okay? It'll give you something bigger than 1 inside here, and so that inverse sine is not defined, And so it will give you an error message there if you try to do this. There will be an undefined thing, and of course it should be because there's no such triangle. If in fact this is defined, then this one at B1, the acute angle will always be a possibility. But sometimes this obtuse angle there, its supplement, is a possibility as well. And the way you can check is just take the angle A and add it to B2. As long as that's less than 180 degrees, then there is room for the third angle, and this ambiguous case will be showing up. Okay? So we have to go, if both of these are still possible, we have to go forward with that. So with that B in hand, now we have all that. We can find the angle C by C or C1 is by subtracting 180 degrees minus A minus B1, or pi minus that if we're using radians. And so we can find angle C. And then to find side C, we use law of sines like this to find side C. And of course, once we have A and B and angle C1, we can find the area. Now, if we can't eliminate this yet, then we can use this to go forward and use the same setup to find exactly the same computations, but with a different value for B, to find a different value for C, and a different value for side C, and a different value for the area. And so we can solve the triangle in this case, but these techniques using law of sines and law of cosines allow us to find the exact measurements of this, but there are two congruence classes in some cases. Okay, and we'll leave a proof to a later time.